Historically, branch of geometry played a very important role in developing new mathematical ideas even outside geometry. Let us concentrate on the topic of tangency in geometry. If we have a circle, which is a very common shape in geometry, and it exists on a plane, then we can also have lines in that plane. Now, in what relation can those lines be to the circle? Well, one of the boring cases is when the line does not have any common points with the circle. It doesn't cross the circle, right? If we move our line downwards, we may arrive at this case. This line has two intersection points. This line is called a secant line. But of course, it's very intuitive to realize that there is a case in between these two when a given line just touches a circle. And this is called a tangent. Just touches a circle. So for a circle, it is very easy to define what a tangent is. L is a tangent for our circle C if and only if the intersection of this line and the circle is just one point. Call it x0, y0. This is some figurative notation, but it should be clear what it means. Now, of course, circle is not the only shape we can have, so natural question would be, does this definition work for other curves? And let's have an example of a familiar parabola, right? I'm drawing it without coordinate aces, but it's fine. So we want a line to only have one intersection with our curve. So that means I can draw this vertical line. It will never intersect any of my branches, and it only has one common point with the parabola. So it perfectly satisfies our definition. So is it a tangent? Well, of course it's not a tangent, right? Because something about this line doesn't seem like it touches the graph, right? It doesn't seem like it's tangential to our shape. We would much rather prefer this horizontal line to be defined as our tangent. This is a true tangent. When mathematicians realized that this was a problem, they decided to come up with a different criterion for a line to be classified as a tangent. And here it is. L is a tangent for a curve at a specific point if and only if L is a close linear approximation of a curve at that point. Now, of course, this all goes to inverted commas because this is just intuition. So what does this intuition actually mean? Well, let us concentrate our attention again around this point. Let me pick a small neighborhood around this point. So I'll just go a bit to the left, a bit to the right. If I magnify this picture, I get something like that. So the question is, which of these two lines looks more like this shape? Is it this vertical line or this horizontal line? Well, of course it's this horizontal line, right? If I pick the same neighborhood, for my calculations, I can assume that this curve is just a line, right? And if I shrink my neighborhood even closer, my line becomes even closer. So this is exactly the intuition which we are going to follow and formally develop. So let's make it formal. Let me again have a function. Looks something like that, maybe. And I want to approximate it locally at a point x with my tangent. So at point x, this function has a value of f of x. And to define my neighborhood, I give it a small increase. And this point is now x plus delta x. So this length is just delta x. So this point gets mapped here, and the value of a function is f of x plus delta x. So now pretend that I have a tangent. Yes, I haven't defined how to build it yet, but suppose we have it. So how can I make sense of this intuition? Remember that I want to be able to approximate this value only by knowing the value of f at x and my tangent line. Well, let us actually see what f of x plus delta x is composed of. Let me continue this horizontal line. Well, first of all, I see that I have to add f of x, right? And then there are two bits. There is this vertical distance between f of x and f of x plus delta x that is split in two parts by my tangent line. So what is the value of this increment? Well, let me redraw this triangle. So I'm interested in this side, but I know several things. I know that this angle alpha is the angle that represents the slope of my tangent line, and I know that tan alpha is the slope, right? This is very easy to realize. And then I also know that this side has length delta x. So by using simple trigonometry, I realize that this side is delta x times slope. So make sure you understand this trigonometry. Write it down yourself and make sure this is clear. So this increment is slope times delta x, and we have a remnant increment here. So we know this increment now, so we can add it onto here, slope times delta x. And what happens with this guy? Well, notice that as I decrease delta x, this small increment decreases in the same way, right? The slope is constant. So as I decrease delta x, this increment decreases by the same magnitude. But this guy above decreases faster, right? Because if I had a straight line here, and this was my f, then it would also decrease linearly with delta x. But we have a curve, and the curve, in some sense, forces this increment to decrease faster than delta x does. Translating that to mathematical language, we want to be able to write that this increment is O small of delta x. So if you're not sure what O small means, go back to the first part, but what it really means is that it's a function that decreases faster than delta x when delta x tends to 0. So here we consider delta x tend to 0. So let us rewrite everything in a clean way. We say that L is a tangent at a point x, f of x, for a function f, if and only if given delta x, our increment that is more than 0, we can write that the value of a function at a new point in the neighborhood of x can be approximated by the value of an old point plus the slope of L times delta x, so it is some linear term, plus O small of delta x, so plus a function that decreases faster than delta x does. And we have to specify that here delta x tends to 0 to make sense of what we mean by O small. So just to restate, we want this function to be equal, the ratio of this function to delta x, taking the limit as delta x tends to naught, has to be 0. So let's have a very easy example. We're just going to have a linear function, say y equals kx, right? So if we fix a certain point x naught, we get kx naught. Let us increase it by delta x to get x naught plus delta x. So what do we get? We get that f of x plus delta x is simply k of x plus delta x, right? We can just plug it in. So does it satisfy this definition? So let us rewrite this. F of x plus slope of L times delta x plus O little of delta x. So this is our general expression, but in terms of this specific function, f of x is kx, the slope is just k times delta x. So notice how the tangent to a straight line is just itself, right? And actually, as we consider this change, we notice that this increment here is just composed of one component. There is no that term notice how this increment here is composed of just one part, unlike we had in our previous consideration. So actually, this function O small of delta x is identically 0, right? Taking k outside, we exactly get f of x plus delta x. Okay? So this definition definitely satisfies what we expect from a straight line. Right. now you need to understand that this definition is reasonable, but it does not provide us with a method of constructing tangents. So our next question is how to construct tangents. We will, of course, use techniques from calculus, and limits will help us. So here's what happens. We again have a function. We want to construct a tangent at the point x. But what is easy to construct are secant lines, right? We just draw lines that have more than one intersection with our curve, but then we move this point closer and closer to x. So we have this point here, draw another secant line, and then make it even closer, another secant line, and we want our tangent to be the limit of all these secant lines, right? So the concept of a limit allows us to do it. So what characterizes a line? Line is characterized by a slope. So line can be defined by its slope. And since we know that we begin at this point, xf of x, we can figure out the constant component in our line equation. So what do? Let us calculate the slopes of these secant lines. So if we have x plus delta x here, then the slope of a secant line is, by well-known formula, f of x plus delta x minus f of x over difference in x delta x, right? So now, remember, we take this point closer and closer, so we shrink the delta x increment. So we want to take the limit as delta x tends to 0. And if this limit exists, right, I mean, there are functions for which this limit will not exist, and we'll show it. If this limit exists, we call this limit f prime of a function f at a point x. This is a derivative of f at x. So I think that here a non-example is going to be helpful. Let us consider a function f of x equals absolute value of x, and we want to know whether tangent exists at a point 0. So my tangent should be an approximation in the neighborhood, right? So nothing forbids me in taking delta x positive or negative. So let us try taking positive delta x and calculating this limit. What do we get? We get that as delta x tends to 0, f of 0 plus delta x, remember that my x is 0, minus f of 0 over delta x. What is it? Well, using the definition of a function, we can write that. And since delta x is positive, and as it decreases, it also stays positive, I can drop the modulus sign and get that it's actually constant ratio, so it is 1. So by this right-hand sided philosophy, if you like, my tangent is supposed to be this line. Let me try and approach our point from a negative direction. So let us now have this delta x. What is the limit now? This limit is delta x tends to 0 minus, if you like, to symbolize that it's coming from the negative direction, is now delta x minus f naught over delta x, which is again this. But since my delta x is negative, when I open or remove my absolute value sign, I have to bring it with a minus, and actually it is -1. So from one side my tangent should be this, and from another point of view it should be this. Of course these lines are not the same, so at 0, 0, f is not differentiable. Now, I didn't really say what differentiability means, but it's very easy. If f of x has a derivative at a point, it's called differentiable at that point. Okay? So an exercise for you is to show that f of x equals x squared has a derivative at every point. So now, what is a differential? Remember, in our intuitive definition for what a tangent should be, we wrote that the new value of f is old value of f plus the slope times delta x plus a little of x. And since we noticed that this part gives the main contribution to our new value, right? This function is smaller with respect to delta x than this. This is called the main part of increment of f, and it's given a special name. It's called a differential. So we have our intuition, and just now we discussed a construction. So do they actually match? So we have the most important theorem in the beginning of calculus, which is that f of x plus delta x can be written down in this form if and only if f has a finite derivative at x. And if this happens, we know that the slope here equals exactly f prime of x. So this is the most important theorem that connects our intuition and the way we construct a tangent. So let us prove one direction of this theorem. If we assume that this is true at some point x, let us first subtract f of x from each side to get this. Now, if you recall how the derivative should look like, we know that we now must divide through by delta x. It is non-zero, and we get slope plus O little of x, delta x, over delta x. And now, let's take limits on both sides. So as we take a limit, this guy tends to the slope, right? Because this is O little of delta x, so this guy disappears. But by definition, if this guy has a finite limit, slope is finite, then slope is f prime of x. And this limit exists and is finite, right? So it's important to realize that in this definition, I do not allow my slope to be infinite, because then I cannot guarantee that this term tends to zero, i.e. I cannot guarantee that this right-hand side converges to my value. So once again, I have shown that this limit is finite, but I know that if it exists, then it equals exactly f prime of x. So this direction is done. Let's begin the other direction, and I will let you finish it. So we know f prime of x exists. So by definition, we know that the following limit exists. What if we now subtract f prime of x, I mean it's a number, from both sides to get this limit minus f of x, f prime of x equals 0. Now, if we bring this guy on top, if we combine it with our fraction, we get this fraction, when this fraction tends to 0 as delta x tends to 0. What does this remind you of? Well, this exactly reminds us of O little of delta x, right? Here on top, we have a function that is O little of delta x, because when we take the ratio of it with delta x, it tends to 0, right? So that means we can rewrite this function on top as O little of x, and then it's just a bit of algebra to recombine the terms and demonstrate that we can write our function in this form. So we are done. We have connected our intuition for what a tangent should be. We have provided a method of constructing a tangent, and we have shown that they are actually equivalent. And what's coming is that in R2, things are different.